Okay, so we have already seen the notion of an algebra over a field, an associative algebra. So let us now today see how we can use this notion to know some things about linear transformations on finite dimensional vector spaces. So in the beginning, there are some preliminary considerations. Suppose that A is an algebra over a field F that has a unit element E. So it's not an arbitrary algebra, I mean it is, but it has a unit element E in it. Also, let us consider a polynomial Qx over the field F. That means it's an element in the polynomial ring Fx. Then for any algebra element A by the symbol Q of A, we mean the following element of the algebra A again. This is the element that QA denotes. So let us first try to understand what this is. It is just a notation. So what this is saying is that you have a polynomial Q over F, the underlying field of the algebra from where the scalars are coming, and you have an algebra element A. You can then evaluate the polynomial Q at the algebra element A. By that we just simply mean replace x with A. That's what we normally do when we evaluate a real polynomial at a real number. So that same idea can be applied here also. And because we need, you see, it should be consistent. Okay, everything should be consistent. This is a sum in the algebra A. So that means the terms in this sum should be elements in A. Are they? Let us see. Any power of A where the exponent is a non-negative integer, of course, is defined in the algebra because A is a ring, so there is a multiplication. Using that we can have, we can meaningfully define any such power. And then that again is an element of A, which then you can multiply by a field element alpha I. That is also available to us in the form of scalar multiplication, because an algebra, besides being a ring, is also a vector space. So that's how all these terms are again elements in A. But in order to have this last term also, the first term also an element of A, we need this E here, which is why we need a unit element E in the algebra. And there sum then again is an element of A. So this element we are going to denote by Q of A. Now it may or may not happen that this Q of A is the zero element of the algebra. If it does happen, then we say that A satisfies Q of X, Qx. Or if you want, you can also say it in the other way, that the polynomial Q of X annihilates A. It just gets rid of A. It makes A 0. Okay, in that way also you can think of it. Okay, now when we come to linear transformations, in particular, we are now going to study linear operators. I have already discussed that a linear operator on a vector space V is a linear transformation of this type. Now, if the vector space is finite dimensional, what is it that we can do to study this function? Because this is after all a function, right, which preserves some structures. Immediately, if we just simply think of it, nothing comes to our mind. But there is a property of algebras that will help us in doing so. A property of finite dimensional algebras. That is where we are going to start today, in the form of this lemma. This is going to be lemma 612. So the statement basically says this, that suppose A is an algebra over F. I am not writing everything down. A is an algebra over F just like this one, which has a unit element E, and also as a vector space over F. Suppose A is finite dimensional and its dimension over F is n. Okay, then any element A in F, oh sorry, not in F, but any element A in A satisfies a non-trivial polynomial over F of degree at most n, that is at most the dimension of n. This is important, non-trivial, because if you think of the trivial polynomial, which is the zero polynomial, that you can understand will be satisfied by any algebra element. Any A, whatever it is, if you choose from capital A, if all the alpha i's are 0, then of course trivially this combination is also going to give you 0. It is 0. So that is nothing interesting, it always happens. But if the algebra is finite dimensional, then there is a non-zero polynomial over F that any element A will satisfy. That means for an element A, you will find one such polynomial that A will satisfy, and the degree of that polynomial also cannot be more than n. It will be at most n. Now, how can we prove this? So, for a proof, you first consider any algebra element A. Then what we are going to do, we are going to consider these elements which are powers of A. These powers of A. I think in the text it is M. Although it does not matter, but still let me just write it as M. Okay, so now we see a list of how many elements? You see, we see a list of M plus 1 symbols here. Excluding this E, there are M powers of A that you can clearly see. But if you include E also, that becomes M plus 1. And because we are in a ring with unity, this can also be thought of as the 0th power of A. Okay. Now the thing is that in this list there may be repetitions. Maybe some power of A that you see here is equal to some other power, in spite of the symbols looking different, that is having different exponents. That can happen. What happens in that case? The author actually has not discussed that condition, okay, or that case in which there may be repetitions. Maybe he felt that we should be able to figure it out, or it is something trivial. Okay, so he assumed, Herstein assumed that all these elements are distinct. That is another case, but we have to see this one also. It is in a sense very easy. If all the elements in this list are not distinct, then what happens? Then of course some a to the power I is equal to a to the power j. For some integers I and j satisfying these inequalities, that is I and j are distinct, but the the ith power and the jth power of a are equal. In this case, A satisfies the non-trivial polynomial x to the power j minus x to the power I. Okay, why is it non-trivial? It is non-trivial because these are distinct powers of x. That is because j and I are different. So they do not cancel, as polynomials, they do not cancel each other and make this polynomial 0. That is not happening. Moreover, their own coefficients, none of them is 0. This one has coefficient 1, this one has coefficient -1, none of which is equal to the 0 element in the field. So this is a non-trivial polynomial, and This equation clearly shows that if you replace x with a here, then you are going to get the zero element of the algebra. Moreover, you can see that the degree of this polynomial is j, because that is the larger one, and that is not exceeding m. So actually whatever we are claiming here, we are in fact getting already in this case. So now assume that all these elements are distinct. The non-distinct case we have already handled, it is done. So now let us consider the distinct case. Okay. Now we know that in this list actually there are m plus 1 elements due to distinctness. But you see that as a vector space, A is m dimensional. So a previous result tells us that the set of these elements will be linearly dependent. In fact, that result is, I think I have the number with me. Yeah, lemma 424 by lemma 424 this set is linearly dependent over if you can, or you may choose to not write also, because if now is the only underlying field. If there is more than one field, then of course you have to mention over which you are considering dependence or independence. So that means there exists linear dependence. Means what? There will exist scalars in the field. How many scalars? As many vectors you have. Not all of which are equal to 0, but the linear combination they are going to give us of these vectors will be 0. Because there is an E, so we start the index with 0. Not all 0. See, not all 0 does not really mean that all of them are non-zero. No, there may actually be some 0 alpha i's. But what it says instead is that all of them are not simultaneously 0. That's what we mean by this. Okay, so this is coming from linear dependence. Thus, A satisfies the non-trivial polynomial, this one, in fx of course. Why is it non-trivial? Due to the fact that not all the alpha i's are equal to 0 simultaneously. Note that this is at most m. See, we may be tempted to, just by looking at the polynomial qx, we may be tempted to conclude that its degree is m. But do not forget that we do not really necessarily know whether alpha m is non-zero or not. It may be 0, who knows? We only know that at least one alpha I is non-zero. So if it is really non-zero, then the degree is m, otherwise it is less. So all we can say here is that the degree is at most m. Moreover, because it's a non-zero polynomial, we are able to talk about its degree. In this text, the author has not defined any degree for the zero polynomial. Although in some algebra texts you will find that there the degree of the zero polynomial is taken as say -1 or minus infinity, but here we do not need that. Okay, so then that's just it. We have found a non-zero polynomial which the chosen element satisfies and whose degree is also at most m. Now this fact about finite dimensional algebras is in fact the thing that is going to help us in our to even start the study of linear operators, because it has an immediate consequence in the form of a theorem that now we are going to see. But I think I need some ink first. This theorem that now we are going to state is just a restatement of this lemma, but in a very particular algebra, those algebras that we are interested in. Remember that this lemma requires the algebra to be finite dimensional. Okay, so let me just state the theorem. This is the theorem. This theorem starts off just like that one, but of course not with an algebra in the beginning itself. It starts like this: let V be a vector space over f of dimension n. Let T be an element in A of V. Then T satisfies a non-trivial polynomial over f of degree at most n square. This is the theorem. So what I said just now is that this theorem is simply a restatement of that lemma. Let's try to understand how. So you may remember this thing from the previous sections on vector space theory. Say we have two vector spaces V and W over the same field. The underlying field of scalars is the same. We have then already considered this thing, namely the set of all linear transformations from V into W. We introduced an addition and multiplication by scalars on this set, and that made it into a vector space. But in the special case where these two spaces are the same, we have also introduced a multiplication of two linear transformations, which is just their composition, and that turned this into an algebra over the underlying field. And in fact, this is the thing we are denoting more briefly by this notation A of V. So what we are now seeing here is that V is an n-dimensional vector space over F, and T is a linear transformation, which we have decided to call a linear operator when the spaces are the same. Then T satisfies a non-trivial polynomial over F of degree at most n square. So if you remember, when we studied this thing in the vector space theory, we proved one result, that if these originally are themselves finite dimensional vector spaces, say V is n-dimensional and W is m-dimensional, then this vector space of linear transformations from V into W itself is finite dimensional, and its own dimension is the product of n and m. If you apply that to this, then this becomes n square, because V is n-dimensional. So now you can see that in that previous lemma which we saw just now, in that lemma you can replace the algebra by this algebra, and then it is just simply the statement of the lemma itself. There you had dimension m, here the algebra is n square dimensional. Okay, so any algebra element is going to satisfy a non-trivial polynomial of degree at most n square. But you keep in mind that all the conditions should be satisfied. Is this a unital algebra? Is there a unit element? Because we need a unit element. We have seen in that lemma. Yes. What is that unit element? It is nothing but the identity map, which maps every vector onto itself. We know that in this ring, this is the unit element. So yes, it is a unital algebra, and so by the previous lemma we are directly getting this. There is no need to show any proof or anything. It's almost immediate. All right. Now this fact has an interesting consequence, and this is the consequence. Because any such element is now going to satisfy at least one non-trivial polynomial of degree at most n square, there will be one with the smallest possible degree also, and such a polynomial will be called a minimal polynomial for the linear operator T. But before we get to that, before we write that down, let us note one more thing also. Although we now have this bound n square on the degree of that annihilating polynomial for T, but we can actually improve this bound by claiming that there will be again a non-trivial polynomial, may not be the one this one is talking about, maybe some other polynomial that T satisfies, whose degree is in fact at most n. So we will see this later when we see this thing, Cayley-Hamilton theorem, which you may already know. Okay. So we will see why this is true and how this is true. Right now, all we know is that there is at least one such polynomial, and that is enough for us right now. So what we are saying that if there is one such polynomial, then there will also be a polynomial of smallest possible degree, and that will be called a minimal polynomial for T. A polynomial over f of smallest possible degree is, that T set, I need to mention that also, that T satisfies is called a minimal polynomial for T. If you want, you can write over f. Okay, but again, if only one field is involved, there is no need to mention this over f. You may be thinking, I have not written anywhere in this statement the fact that the polynomial needs to be non-trivial. However, we are talking about its degree, no? And we have defined degree only for non-trivial polynomials. So automatically, this means the polynomial has to be non-trivial. Also note one more thing, a minimal polynomial. Maybe there are multiple distinct polynomials of the same smallest possible degree that T satisfies. All of them will be minimal polynomials for T. This A can be made D provided we impose another condition. If you require that the polynomial is also monic, then this will become actually a unique polynomial. We will come to those things later, okay. Now, let us see something else about this algebra, which is in fact something that we already, we may not have really discussed in depth about what now I am going to discuss in ring theory, namely the notion of left and right inverses of ring elements. Let us see what those notions look like here in this algebra, because this is also a ring, right? So this is the thing. Next definition. Suppose T is any element in our algebra A of V, and let me also mention that here V need not be finite dimensional. V is any vector space. At least in this definition, V is any vector space, although the results that we will see ultimately will need finite dimension, but the definition can be made in any vector space and the resulting algebra of operators. T is called left invertible if st is equal to 1 for some s again in A of V. This one is that unit element in A of V, that is the identity map from V to V. If you find for this t again an algebra element S such that st is equal to 1, then t is called left invertible, and in that case you can understand that S will be called a left inverse of t, a left inverse. Maybe there are more, who knows. T is called similarly right invertible. If there is a right inverse. If tu is equal to 1 for some algebra element u in A of V, and finally t is called invertible or regular if it's both left and right invertible. Okay, now regularity or invertibility of t will have a consequence on these elements S and U. Let us see what. Actually, this will imply that S and U have to be equal. How? Suppose T is both left invertible and right invertible. So there exists an S for which we have this, and also there is a a U for which Tu is 1. For some S and U in A of V. Our claim now, or the author's claim now, is that S must be equal to U. This is how it can be substantiated. In place of S, you can write S1, of course, because 1 is after all a unit element in this ring, the unit element. Now, in place of 1, you can write Tu. Because our algebra is associative, or because we know that composition of functions is associative, so you have this. But St is also 1U, so this is equal to U. So you see that if T is invertible or regular, then these two elements have to be the same. But there is another fact also. Fine, these two elements are same, but can there be more than one such elements, same elements? Say you have S1 and S2 in A of V such that these are true, that both of them act as inverses of T. Although we haven't said, we haven't defined the word inverses, we are coming to it. Such that S1T equal to TS1 is equal to 1 and S2 T equal to TS2 equal to 1. Okay, so S1 acts as our S and U. They have already been proved to be equal, and so does S2. But then what happens? You see that then S1 acts as a left inverse of T in this sense, and S2 acts as a right inverse of T in this sense, and we have already proved that then they are equal. So that is why in that case S1 has to be equal to S2, and this uniqueness finally lets us define the inverse of T when it exists. When T is invertible, St is equal to Ts is equal to 1 for a unique S in A of V. We write this S as T inverse and also call it the inverse of T, although this has not really been written in the text, only the symbol is given. But it's okay, we already know that we can call it the inverse of T due to this uniqueness. Now, of course, because the definition has been defined like this, and also it has been defined for any A of V, that means our V need not be finite dimensional. And now we are going to see that in such a case, in an example, we will see elements which may not have left or right inverses. Let's see. So next, that text gives us this example. Say you consider this function S from Rx into Rx, which maps every Qx onto its derivative. There are some things that need to be explained about this. We already know that the set of real polynomials is a vector space over the field of real numbers. And what we are doing here is that S is just simply differentiation, but you should be careful. You should be a little careful about interpreting this properly. When we think of differentiation, immediately limits come to our mind, right? We think of things like this. Say this is equal to this. Things like this come to our mind, and you can interpret this in that way also, because the field involved is R, but do not do so, because the same thing can also be done, for example, over a finite field. Do you see what kind of problems will possibly arise in such a case if you try to think of limit, or say there is some arbitrary field here? You see, immediately just by looking at this you do not see any problem. However, what is the meaning of limit? In the definition of limits itself, you need to be able to decide when q of x plus lambda is near q of x, the distance between them should be less than epsilon if delta is small. In what sense? In the sense of a metric, right? And those things may not be available here. So instead of thinking in terms of limits, actually it's much easier. No matter what the underlying field is, this is how you should interpret it. That is by the form of the answer that you normally have when you differentiate a polynomial. That is defined to be what the differentiation is, which actually does not need any limit. So you do understand what I am trying to say here. In that sense, the author has defined another operator, T. And that operator involves integral, similarly interpreted. I think it's taken from 1 to 1 to x, not from 0. Okay, and using the, or I should not say using the familiar rules of algebra, calculus, but rather rules that are similar to the rules of calculus will show you that this s and t are both linear operators on V. Of course, in our case right now, in place of V we have Rx. This is a routine, although it may be a little tedious task to verify this, but it can be done. That's not the important part. The important part is now this. Just like this, verifying that S and T are both linear operators, one can also verify that Ts is equal to 1. In other words, if you take any real polynomial qx, then you apply Ts on that, that is, first you apply this and then you differentiate, you will be able to show that you get qx back. So Ts in fact is 1, which tells us that T is a left inverse of S and S is the right inverse of T. But if 1 is the constant polynomial in Rx, then on 1 if you apply St, what does that mean? Applying S on 1 first and then applying T on the result. Differentiating the constant polynomial, just like, because this is how we are defining S, you still get 0, the 0 polynomial, on which when you apply T, you get 0. And this is not equal to the polynomial 1. So, St is not equal to 1. Okay. Now, does this inequality or non-equality immediately imply one thing? Say, we will get confused if we think about S and T simultaneously. Let us concentrate on T. Suppose T is the element that we are talking about. This equation shows us that S is a right inverse of T. This one does not immediately tell us that T has no left inverse. All it says is that S is not a left inverse of T. However, if you still suppose that T has a left inverse, say L, then by what we have done here, L should be equal to S, but then you are getting St equal to 1, which this one does not permit. So that is why there is in fact no left inverse. So T, despite having a right inverse, has no left inverse. T is right invertible but not left invertible. Similarly, S is left invertible but not right invertible by a similar argument like this one. And this is happening due to the fact that this is not a finite dimensional vector space, and another result that we will see afterwards. Okay. So this is that. And there is something else I forgot to say while I was talking about minimal polynomial. Suppose T is a linear operator on a finite dimensional vector space. V has finite dimensions, okay. Then we know that T has a minimal polynomial P of x, say. There may be others, we have already said that this is not necessarily unique, but it has the smallest possible degree of any non-zero polynomial that T satisfies. Now suppose you have another polynomial, any polynomial in fact, that T satisfies. And it's also a non-zero polynomial, okay. Such that h of t is equal to the zero operator. Then can we say something about the relationship between px and hx? Yes, we can. If you recall, we showed that fx is a Euclidean ring, that is in which you can divide any element by a non-zero element. You can similarly divide hx by px to get a quotient polynomial qx and a remainder polynomial rx, where either the remainder is the zero polynomial or it is non-zero, in which case its degree exists and is less than the degree of the divisor polynomial. Alright, now let us see what we get if we replace x by t. Obviously h of t is 0. Where is it? Here. But that is equal to q of t times p of t plus r of t. Since t satisfies the polynomial px also, so this term vanishes and we are left with r of t. So we see that t satisfies r also. Now looking at these two cases, what do we see? If it happens that r is a non-zero, a non-trivial polynomial, then t is satisfying r, but at the same time r has degree less than the degree of a minimal polynomial. Can this happen? No, because that would contradict the minimality of px, or rather, more specifically speaking, the minimality of the degree of px. So that's why this case cannot happen. That is, r of x has to be equal to 0, but then px divides hx. So this is one fact that is used heavily in linear algebra, namely that any minimal polynomial of a linear operator divides any annihilating polynomial, any other polynomial, or maybe this one itself, okay, any polynomial that t satisfies. In fact, if one considers the set of all polynomials that t satisfies, then this becomes an ideal in this Euclidean ring, and as such it is a principal ideal, which is in fact generated by such a minimal polynomial. Now to end the video, I am going to state a result which links a minimal polynomial of a linear operator with its regularity or lack thereof. It's very interesting. Let's just see the statement, and with that we are going to end. So underlying all these things, actually there is ring theory, or rather a combination of rings and vector spaces. So the result that next comes is this. Suppose T is a linear operator on a finite dimensional vector space. Then it has a minimal polynomial, you already know. Say this is its minimal polynomial. Okay. For T. Then what this theorem states is that T is invertible or regular if and only if this constant term in our minimal polynomial is non-zero. Okay, so if somehow someone is able to find a minimal polynomial for T, then just by looking at the constant term one would be able to say if the operator is regular or not. And I forgot this part also. In the definition, after the definition of regularity, this one line comes: if T is not regular, then it's called singular So that means similarly, because this is if and only if, the constant term in a minimal polynomial of a singular linear operator must be equal to 0, and conversely also. And with that, I am going to end today's video. Our next upload is of course according to our schedule. That means today is what? I think today is Thursday. So the next upload is this coming Saturday. So see you on Saturday. Until then, this is me, Lucifer from a mathematical room. Have a nice night.